Hey, freshmen. It's good to be back again. This is our second lesson. It's great. We're making good headway. This is Psalm 116, verses 1 and 2. I love the Lord because he has heard my voice and my pleas for mercy, because he inclined his ear to me. Therefore, I will call on him as long as I live. God, I do call on you today that you would help us. In this trying time, let us lean hard on your son, Jesus. Amen. Well, we talked about Archimedes last time. Let me tell you what he said. He said the weight of the fluid displaced by an object immersed in it is equal to the buoyant force underneath that object. He was supposedly in a bath, and as he lowered himself in the bath, he saw more and more water being displaced until it quit being displaced because he was floating. It wasn't being pushed out of the way anymore. So if he weighed 160 pounds like me, he concluded that there must be 160 pounds underneath him to keep him floating. So let's just suppose that he gathered up all the water that overflowed from this tank that was completely at the top with water, and he weighed that. What would it weigh? Well, it would weigh 160 also, because the weight of the fluid displaced by an object immersed in it. Immersion means either floating or sinking, either floating or submerged. They're both immersion. So he went ahead and if he were to weigh that, it would be 160. So in the case of a floating object, they're all three equaling the same. And tomorrow, we're going to prove that with some molding clay, but not today. Today, I'm going to talk to you a little bit more about this right here. You remember the formula to calculate the density of an object? Well, now this object will sink. It will submerge, not float. So we're going to go ahead and lower it down in there. And it doesn't have, it weighs 500, as you can see on the spring scale. It's not going to have 500 grams of force pushing up underneath it because it doesn't float. It's going to have less than that. So let's go ahead and lower it in there. I've primed this overflow can before you got here. Glad you came. Here we go. Further down, the more water overflows until you're all the way down and submerged. Now, you would have been doing this yourself, except that we're not in school. Sorry about that. We'll go ahead and set that aside, and we'll take this and we'll measure it, the volume of it, in this graduated cylinder here. You know what the volume is? Right there, 63. And so 63, if we want to go for density, density is mass divided by volume. We would say the mass of that 500 gram mass is 500 grams, and 63 would be its volume, 63 cubic centimeters, or 63 milliliters of water was displaced. Now, when we take that 500 divided by 63, 500 divided by 63, it equals 7.9, which is the density of iron that thing's made of. Grams per cubic centimeter. Now, we could also say that this is the weight of the object in the air, and this is the weight of the fluid displaced by the object, or the weight of buoyancy pushing up underneath it, the force of buoyancy. Or we could say that it is the loss in weight. So the weight over the loss in weight is equal to the density. And that's the big discovery that Archimedes came up with. And then he wrote his principle from that. And his principle, simply stated, is right here. You can see that on your lab form. By the way, I attached this lab form in case you didn't have it. And so you can just look on your LMS. You can copy it or you can just split screen it. I don't care, whatever. So it says the weight of the fluid displaced equals the force of buoyancy pushing up underneath the object. That's Archimedes' principle. All right, question number 1 in lab B, right here. What's the volume of this little boat? Well, if you want to know the volume of that little boat, it's very simple. That's a cylinder. So you're just going to measure the diameter. That's exactly 3 centimeters. And you're going to measure the height. And that is exactly, let's go ahead and do this again. That cap on there. That's exactly 5.3. 3 by 5.3. Now that's the volume. Okay, so this is the diameter, and that is the height. And pi times diameter is the circumference. And so if you can get, what you need is the area. You need the area of this times the height. Excuse me. I messed up on that. I'm entitled to that, right? So what is the formula for area? Isn't it pi r squared? So if the diameter is 3, we're going to take pi times 1.5 squared times 5.3. Let's see what that gives us for the volume of this container. That's our little boat. Okay. Here we go. Pi, that's my shift button here, times 1.5 times 1.5 times 5.3 equals 37.46. I'm going to call it 37.5 cubic centimeters. That, my dear, is the volume. Now, there's another way to get the volume of this thing. The whole purpose of this is we want to calculate the density of this boat with some cargo inside. So let's put some cargo in there, a whole bunch, just 13 pennies, enough so that it'll sink. And we'll use the water displacement method. Displacement means push out of the way. So we'll get this overflow can primed up real good here. Don't forget to throw away the excess. I sure wish you could have done this lab. It's a good one. Okay. And we're going to go ahead and lower this in there. There we go. Good night. And we're going to use this 50 milliliter graduate to see what the volume is. Because shouldn't the volume be the same as the amount of water that was displaced when you lowered it into this overflow can? I would think so. What's the right answer? Or at least we think it is by doing the measurement calculation. Wasn't it 37.5? And right here, we got exactly 40. 40. So there you go. Little difference. Which one am I going to use? I don't know. Let's just use 40. That's a nice round number. So you can either get it by measurement or by overflow, which is due to displacement of 40. Okay, so we're going to put a big old fat 40 right there. Now, what's the mass? We're going to go ahead and measure the mass of, according to lab B, 3 pennies inside the boat. Oh, the boat's in there. Come on back to me. I don't know about you, but I'm having a great time. So here is 1, 2, 3. Now let's measure that. Here's a balance. That measures 13.9. 13.9. So what's that? 13.9 divided by 40. 13.9 divided by 40 gives me 0.34. Grams per cubic centimeter. Is that the same as approximately 1/3? Is 0.33 about 1/3? Say yes. Yes. Okay. You got that right. So here's the point I'm going to try to make. When I lower this thing, this boat with its cargo into this graduated cylinder. Oh, no, that isn't it. That's a beaker. Into this beaker, you're going to see that about 1/3 of this boat is underwater. You see that? About 1/3 of that boat's underwater. So the amount of the boat that is submerged in the water will give you a kind of a approximation of the density of that boat. Is 0.33 less than 1? Yes, of course so. And then that is a good indication that it will float in water. If the density of the object is less than the density of the fluid that it's immersed into, then it will float. And the density of water is 1, and so 0.33 is less than 1, so it'll float. Now, what does it say in our lab? Put 9 pennies in there. Let's see if this keeps working. 1, 2, 3, 4, 5, 6. 6 and 3 make 9. Let's get a weight. The weight is 28.8. And let's change this to 28.8. 28.8. Now divide that by 40. Okay, here we go. 28.8 divided by 40 equals 0.72. 0.72 is about 3/4, which is 0.75. So do you expect 3/4 of this little boat to be under the water? Yes, Mr. Schultz. Okay, well, let's see if that's truly the case. I'm going to put this in here. And what do you see? 3/4 of that rascal is under the water. That is a good approximation of the density. Now, if we have 12 pennies, that was 9, so 10, 11, 12. 12 pennies. Let's see what happens. Is it still floating? I think it is. Look at that rascal. It's floating, but it's kind of floating in the middle. There's hardly anything above, which is called superstructure, by the way. There's hardly any superstructure above the water line. And so that has become one with the water. So if the density of water is 1, then the density of that boat is approximately 1. It's not a percentage underwater, it's the whole thing underwater. And if I just add a little bit more cargo, this thing will probably sink. And it did. 13 pennies makes it go under. So now the density is greater than 1. So you got this merchant. And this merchant is bringing Toyota Tundra trucks from Japan to the United States and going through the Panama Canal. And he's over in Japan and he loads up his ship with just as many trucks as he can to make as much money as he can. And it sinks the ship down right at the water line. And then he floats his boat over to the Panama Canal, starts to go through the canal in that first lock, they close the door on the lock, and it sinks. Why did it sink? Well, if you're thinking about that, it may have something to do with the fact that the Panama Canal is full of fresh water, while the ocean that the boat started out in from Japan is salt water, which is more dense. And so the boat was able to float in the more dense fluid, but when it got into the fresh water of the Panama Canal, it sank. It's a bad day for the ship's captain. Okay, now, here's what I'm going to ask you to do. Think about this overnight. F, go down to item F and look at it. Float a film canister with 10 pennies in it. Read the level of the water in the small beaker. Then dump the pennies into the water and float the empty canister. Does the water level go up, go down, or stay the same? That's what we're going to do now, except I'm going to tell you a story on how this works. So here's the deal. You guys have any idea what this is? I'll be done here in just a second. So bear with me. By the way, you're going to get more questions on your quiz this time because I'm going to start including section 1. We will not have a test over the entire chapter. We're just going to do these tests after every one of my lessons. And I will include questions from lesson 1 along with a couple of questions from what I just discussed today. And we'll just keep taking these daily tests and that'll be good enough. Okay, here he is, right here. There we go. And here's the dude. That's the dude, and there's the cowboy hat. And there we go. And he's got these big old rocks in there with him. His name's Billy Bob. And everywhere he goes, floating in this pond, there's the pond, he always has rocks in the boat. So here's the boat. Now we got this over here. There we go. Do you have any idea what that is? Yeah, that's a pier. And it appears, like the water is lapping up against the pilings of the pier right about there. Now you got the girl. You always have a girl in the picture. She's got her cowboy hat on too. She's Daisy May. And good old Billy Bob over here asks Daisy May whether or not she knows what's going to happen when he throws the rocks from the boat into the water. And she says, of course I do, because I had Mr. Schultz for science. He says, well, I did too. I happen to know also. My question is, what's going to happen to the level of the water in the pond when he throws the rocks into the water? Now you ponder that over the evening. Try to think about that, and we'll start our lesson tomorrow by taking this boat right here, which has a whole bunch of rocks in it, and floating it in the water, and then we'll go ahead and we'll pour the rocks into the water and see what happens to the level of the water when you put them in there. Okay, you be good. See ya.